Right. Yeah, thank you for the kind introduction, and thank you for inviting me to have an opportunity to talk about my research. So I was asked to give a quick introduction of myself and then present what the generic perspectives of what I work on. So yeah, as mentioned, I'm currently a postdoctoral researcher at the University of Amsterdam, and yeah, the stuff that I work on can be summarized into asymptotic symmetries and infrared physics. So I've sort of jotted down some topics that are relevant for my research. So there's one note here that's called asymptotic symmetries. There's some topics: EMS symmetry, large gauge symmetry, magnetic gauge transformations, dual diffeomorphisms. Another topic here is called soft theorems. There's a bunch of different soft theorems: soft photon theorem, graviton theorem, Lowe's subleading soft photon theorem, Strominger-Cacciazzo subleading soft graviton theorem, and finally Sahu-Senloff soft theorem. So on. Another note here is higher divergences. This has to do with Faddeev-Clé states. I'll describe what these are in a moment. But you'll notice that these are very old topics. Asymptotic symmetry has been studied since the 60s. Soft theorems has been there forever. It's been written down explicitly to all orders by Weinberg in 1962. Higher divergences has been with us forever also. Faddeev-Clé states are states that's been worked out in the 70s. So you could ask, well, why talk about these now? There's recent progress in tying these ancient subjects together, and it's this relative perspective that I'll be focusing on. They go under the umbrella term of celestial holography or flat space holography. So let's talk about each of them. So what is a soft theorem? Soft theorem is a property of scattering amplitudes in gauge theories that can be derived from Feynman diagrams. Can I move this? Yes, yeah. So the statement of soft theorem is this: you take an amplitude in gauge or gravitational theories where you have some number of particles coming in and some number of particles going out, and one of the external legs is a gauge boson. It can be a photon, a graviton, photino, gravitino, or whatnot. Then you study the limit where the energy of that external gauge boson goes to 0. And what you notice is that that amplitude factorizes into another amplitude without the external soft boson times something called a soft factor. And by soft, we mean infrared or low energy. So of course, the momentum is a dimension full object. So it doesn't really make sense to send it to 0 unless you compare it to something. So what we mean by the soft limit is that the energy of this boson is very small compared to all the rest of the legs. And in contrast to the term soft, the energies, the typical energy scale of the other legs are called hard. So the statement of soft photon theorem is that you have an amplitude with the energy k, the momentum k of the soft photon, the polarization epsilon, and all the rest of the hard particles, whatever they may be, electrons, other photons, and so on. You take the limit as k goes to 0. And you notice that it becomes an amplitude of the hard particles that has nothing to do with the energy of the gauge boson times some factor in front. And you'll notice that it's a sum over only the external legs, and it doesn't know anything about the dynamics that go in the bulk. Similarly, you can work out the soft theorem for gravitons, where you have an energy k and polarization epsilon of the graviton. You take the energy going to 0 limit, and you have a sum over the external legs as well. One peculiarity that you'll find is that in QED, or in any gauge theory, the sum is over the charge. Each leg has a charge of its own, while in gravity, the soft vector has a universal coupling kappa, which is like square root of the g Newton. And this is telling us about the equivalence principle, where gravitons couple to all matter in a unifying way.
A simple question.
Yes.
So what is K? K is a 4 vector.
Oh, K is a 4 vector for the photon.
Goes to 0.
Oh, so this is a null vector. So there's an overall scale. Yes. So you can think of the zeroth component, the time component of the vector.
Photon K is actually naturally photon K. A method actually K equals 0 actually.
Yes.
For photon.
For photons.
On shell.
On shell, external X, yes. On shell, yes.
So always K equals 0.
Always K goes to 0, yes.
We don't have to take K equals 0 because he actually on shell photon always K equals 0.
Oh, K squared is equal to 0, but K, the momentum 4 vector can be anything.
K is different from K squared.
Yeah, K squared is the 0,
Yeah,
so that's on shell.
Means energy and momentum simultaneously 0.
Yes. So we have an on shell vector, K squared is 0.
IR limit. Yeah.
Yes, we take the IR limit, exactly. Yes. Another important point is that the soft vector in this limit is divergent because there's a K downstairs. That means there's a pole as we take omega to 0. Well, the K goes to 0 limit. So in principle, there are subleading terms in this small K expansion, which we'll talk about later. But this is called the leading soft theorem, to be precise. There are subleading soft theorems that we will come to in a moment.
So by looking, so the graviton also has some divergent prefactor.
You mean kappa here, or?
I mean, so the denominator is always the same.
Oh yeah, it's always 1 over K.
So it seems it's a divergent.
It's still divergent, yes. All of the soft vectors are divergent at leading order.
I see even for graviton.
Even for gravitons, yes. Any other questions?
And a little bit the thing is that the quantity in the prefactor in the parentheses,
Yes.
that is the dimensionless quantity. Is that right?
There is a dimensionless quantity here, yes.
So kappa is what? 1 over P.
Oh, I mean this thing here, this two momentum upstairs, 2 momentum downstairs. That's dimensionless. Kappa here is square root of
up, but only one the pi dot k is compared to the top line. One line above compared to the usual particle fermions or bosons.
Oh, so this is the electron charge, the charge of the charged particle. So if it's an electron, let's see, if it's a positron is positive V. Here, kappa is like square root of the Newton's constant.
Right.
So it's also dimension full.
So I'm just very bit puzzled by the number of p's. Of course, it's due to the spin too, but there is no. So it's maybe kappa. With combined with the kappa, then it's the same as above dimensionless. I don't.
Yeah. So you're worried that the dimensions of the two things are different? Or?
Right. Usually, I thought. I mean, for any spins, I usually. So if we just understand the spinless case,
yes,
spin-dependent part is a little bit trivial or some.
Oh yeah. So in this leading order in this expansion, the soft vectors don't know anything about the spins that they're coupling to. So if the external X are spinor electrons, or if they're scalar electrons, the soft factor is universal in the sense that it is always the same.
So E vector, EI, is it charge and the polarization or?
Oh, this is just the charge.
Charge, only charge.
Yeah, and epsilon is the polarization vector.
This divergent phenomena is typical in the IR limit.
Yeah, this is universal. You take any gauge theory like Young-Mills, QED, spinor QED, scalar QED, gravity, string theory even. You take a massless boson, you take its limit to 0, the amplitude always factorizes. Yes. Okay. It breaks something. Oh,
The typical scattering process always produce soft photon or soft graviton, yeah? Because
Yeah.
it's singular. Yeah?
yes. So in practice, we have detectors that are able to only measure some region in the momentum space. So there's always some soft region or some infrared photons and gravitons that we are not able to measure.
Could you regularize that divergence?
Yes, I'll talk about how to deal with these divergences in a moment.
Even IR, actually, normalization is possible.
IR renormalization. So this is a little bit different from the UV renormalization in the sense that in the UV, the perspective that we have is that there's a UV theory that we have no idea what it is, but we know how to deal with it. We observe those effects into some coupling constants and wave functions. But in the IR, we know what theory is. It's just that the divergence that arises in the IR is a feature. We don't want to get rid of it. You want to understand where this comes from and why we have this. And this is something that I'll talk about in a few slides. Okay, so because of the Self theorem and its singular behavior, what we find is that any amplitude that we compute in 4 space-time dimensions, and only 4, if we compute, let's say, 2 electrons coming in, 2 electrons going out, we know from quantum field theory that we compute the tree-level amplitude, one-loop amplitudes, all of the one-loop amplitudes, all of the two-loop amplitudes, we sum them all up. And that's the complete amplitude. And it turns out that every loop has some divergence. So all of these are infinite. And furthermore, the infinities all sum up and they exponentiate. So you can sort of isolate the divergent part of each loop and exponentiate them to only find that the amplitude is some finite number times e to the minus infinity, which is 0.
Singularity is always positive.
Yes, it's always positive. Well, yeah, there are signs that all conspire to give you e to the minus infinity. And this is important because it's 0. And we have an operator, the scattering matrix, sandwiched between some states. And for any states, no matter what you choose, it's always 0, which means that S matrix operator doesn't exist in 4 dimensions. Now, how do we deal with this? There is a workaround. The traditional workaround of this is called the Bloch-Nozick method. And this has to do with the questions that arose earlier. There's always some infrared bosons that we cannot measure. And therefore, from statistical mechanics, if we don't know something, what do we have to do? We have to sum over all the possibilities. We take each amplitude with some number of external soft bosons. We sum them all up and then compute the inclusive cross-section. Now, what happens is that the sum over all of these external soft legs exactly cancel with the divergent part that appear in the loops. And at the level of the cross-sections, all the divergent factors cancel out. This is why, even though all the gauge theories are plagued with these divergences, people weren't so worried because the only thing that we measure is cross-sections in the detectors.
E to the minus infinity is actually partition function.
Oh no, at the amplitude.
Amplitude.
Yeah, the amplitude. Yes. So if we implement some IR cutoff, let's say we regulate it with some low energy cutoff in all the loops, let's say epsilon, then what we find is that the exponent is e to the minus 1 over epsilon. And then, e to the log epsilon. And as epsilon goes to 0, log epsilon becomes minus infinity, and therefore this. But now, if you keep that epsilon and compute the inclusive cross-section, you sum over all diagrams with possible external legs with soft photons and gravitons, you sum them all up, and then square it.
I was confused actually. Yeah.
Yes.
Actually, e to the minus infinity is actually amplitude.
Yes.
So in the previous page, actually amplitude is divergence.
Yes. When there is an external soft boson. Now here, this diagram has only electrons. So it looks convergent at tree level, but the loops have divergences. But the solution is that we only care about cross sections for measurements. And we have to sum over everything that we cannot measure, which is there could be a secretly one soft photon that goes out. We don't know about it. And there could be two. There could be like 22 coming in. We have to sum over all of these and then square it to get the cross section. And what happens is all of these possible divergences cancel all of these divergences in the loop. So at the level of the cross section, there's no IR divergence and you get a finite cross section. This is why we can measure all these cross sections in detectors.
So that means the loop contributions cancel the IR divergence.
Yeah, all of these loops cancel everything that comes from the external legs.
All the loops or one third?
All the loops, yes. Yes.
So the trick is that you have to include the possibility that you emit an infinite number of photons with zero energy.
Yes.
So you have to integrate to
Yes.
see that this is
Yeah, this is the Spear's statistical mechanics where you have to sum over all possible amplitudes that you cannot tell apart.
So once you resolve all the IR divergent pieces up to all loops,
Yes.
then it is anyway finite, not one zero. You show.
Sorry, can you repeat the question? So if you have
If you sum over all loops,
Yeah.
even though it is divergent at each loop,
yes.
but what you are saying is that if we add up all the loops,
Yes.
kind of resummation of
Oh yeah, they resum to e to the minus infinity.
that means the infinite loops, then the
Yes.
right after
Yeah, with the infinite sum, that sums to an exponential, which is 0. But if you now include the possibility of having external soft photons and sum over all possible diagrams, you add this plus 2 plus 3 plus all of them, each of which have their own loops, and you square everything to get the cross section. This is called the inclusive cross section. There, all divergences coming from loops cancel all divergences coming from the external legs. So it is really,
each loop there is a matching of tree-level diagram.
yes, for each tree level diagram, there's some number of photons that cancel each other and so on. So you can do this at each ordering loops. Yes.
This is like the internal loops is nothing to do with the soft photons. Seems like that they don't.
Yeah, it looks like it, but yeah, I think the first paper that actually works out all the details is the paper Weinberg in 1960. Yeah, and actually he shows that you add each of these photons and you can attach to like each leg in a different way. There's combinatorics involved. He works out all of these, and you can show that the sum of all these exponentiate to something, and then at loops you can work out all the divergent factors here. They all exponentiate. And once you square them, the exponent squares. So the exponent is usually a complex number, but when you square it to get a cross section, you find 2 times the real part of it, right? And 2 times the real part of this contribution cancels exactly the contributions coming from here.
Why does that happen?
That is that's the why this was an observation. That's like, oh cool, but this was supposed to happen, and this is what I want to convey in this talk.
so the process is unitary.
The process is unitary, yes.
So at the level of amplitude,
Yes.
because you're saying the cancellation is at the level of the cross
Sections.
But and what about
The amplitude is still sick, and this is what I want to talk about. Yeah. Yes.
But actually, it doesn't matter, how many, soft photons coming out, right? So
Yeah, we have to sum over everything because we cannot tell whether there's 10 photons or 20 photons coming out or coming in. So we have to sum over all possibilities and then square them because we cannot tell those diagrams apart. So that was the reason people weren't so worried about infrared divergences. You'll see these in textbooks, but people didn't really care because, as far as measurement is concerned, you can just ignore them. But of course, this is not really satisfactory because we want to work with asymmetric amplitudes. So another resolution that didn't really get the spotlight until recently is called the IR finite states of Faddeev and Kulish. So this was worked out in 1970. And the idea is this.
So
Yes.
can you also extend the block Norsec method to the non-abelian gauge theory?
It can cancel the soft part, but there's collinear divergences that are not resolved. And you have to
Only part of the collinear divergences are cancelled.
yeah.
I looked at.
So it's the energy going to zero divergences that are canceled by this. But collinear divergences can happen when there's finite, even hard particles can give you collinear divergences.
But in the case of the QED, even the there is also collinear divergence.
Yes. So I am only talking about massive electrons in this case. So I want to stay away from collinear divergences because this is something that's still not very well understood. So yeah, in most of my talk, when I say infrared, I will refer to the limit where the energy is going to zero, not where two particles come together in a collinear way. Any other questions? If not, let's look at the other resolution. And this is quite cool because in textbook QFT, what you learn is that you write the Hamiltonian, you break it into two parts. You have the free part, and there's some interaction. And you'll usually assume that if you wait long enough, particles will scatter. They'll be far away with each other. And the interaction vertex, or the interaction Hamiltonian will usually decay, which allows you to assume that the time evolution operator is free at infinity. And therefore, we can use momentum eigenstates as the asymptotic states. So you prepare the momentum eigenstates. You say you have momentum P1 and P2 coming in, P3 and P4 going out, and you basically have Fock states. You sandwich them in between to get the amplitude. But now, the problem is whenever you have massless gauge bosons, so in gauge and gravitational theories, this is not true. The time evolution operator has a free part, but there's something still remaining. I've just schematically put stuff here because the expression is quite complicated, but there's a number, a function of the momentum of the hard particles. It's I times infinity, so it's a phase. So you could say, well, it's just a phase. You can absorb it into the definition of the states, but it's an infinite phase. And then there's exponential of some gauge boson operators. So if it's QED, you have each of the A's, A mu's, and A mu daggers sitting in the exponent. So the actual correct asymptotic states to use are not the Fock states because they don't evolve with this operator. The ones that evolve with this is a momentum eigenstate, which evolves with the free operator. But also you engineer some things in front such that it just cancels these two. So this whole shebang is the one that you have to use for scattering amplitudes. Well, at least that's the argument that Faddeev and Kulish gave, and these are referred to as the Faddeev-Kulish states. And one is a number, but one's an operator, and it's an exponential of an operator. So these are basically coherent states where charged particles, the momentum eigenstates, are dressed with an infinite number of low energy or soft gauge bosons. Yes.
That kind of dressing does not happen for gauge boson itself.
Yes, for gauge boson itself, it gets a shift. There's some subtlety there, but we also understand how that works. But for the moment, the more complication comes for charged particles. And what happens if you now compute scattering amplitudes with these? So you just take this textbook QFT Feynman diagrams, but just instead of using momentum eigenstates, you put these in secretly. And you will find that all the IR divergences cancel. So this tells us that IR divergences, which we thought made all the amplitudes sick, and we only had to work with cross sections, they only came about because we worked with the wrong states.
Is this related? I mean, PFT, we have this Dirac picture to the Schrödinger picture. There is a mapping matrix, and the direction factor is that mapping.
You mean something like Wilson line dressings of the particles, or?
Something like that.
Yeah, so all of this has to do with gauge, the gauge invariance. So there is some ways to understand this in that picture. But I won't talk about that in this talk, but I'm happy to talk about it afterwards. Yeah. Okay, so next.
In the
Oh,
previous page.
yes.
So intuitively, actually, what is the reason in the infinity there is some interaction? So in this t equal infinity, actually v of t goes to 0.
Yes.
So actually no interaction.
V of t goes like 1 over t.
1 over t.
Yes. Now the problem is the time evolution operator involves a time integral of the Hamiltonian. So if you have 1 over t, that gives you log of t, which so it is true that even for gauge theories, the interaction Hamiltonian vanishes.
Why does v behaves 1 over t?
That's something. I guess that's an observation. We compute. Let's say we have a outgoing electron with one photon, and you have an incoming electron. That'll be like computing diagram. This diagram, right? And this would be like P, comma K, S, or I guess V of t, and then P prime. So this would be P prime, P and K. And you can compute this for t going to infinity, and you will find that as k becomes small, this behaves like 1 over t. That's an explicit observation.
This is related to the fact that you have a long range interaction.
Exactly, yes. That's another way to phrase this. And yeah, explicitly long range interaction means the interaction doesn't really die off at infinity, in contrast to what we assume in textbook QFTs.
So in this formalism so far, what is the difference between the pure gauge theory and the massive charged particle gauge?
So we are thinking of, sorry. So let's say just Maxwell theory, for instance, right? Is that what you have in mind?
With electron massive, let's say, rather than
yes.
massive.
The culprit here is the interaction between electrons and photons. So if you just have photons, because photons are not charged, this will not be a problem. In Yang-Mills, gluons are charged. So in pure Yang-Mills, you still have this problem, and you have to work it this way.
So in abelian theory, there is no problem.
No problem, yeah. In abelian pure Maxwell QED, well, in pure Maxwell theory without electrons, we don't have this problem.
So even though there is, the 1 over t of the interaction.
Oh, no, there is no 1 over t, because the 1 over t comes from interactions between charged particles and gauge bosons. So in the absence of charged particles, which is the case of abelian gauge theory, then we don't have this problem. But for, let's say, pure perturbative quantum gravity, gravitons coupled to gravitons, and we have this problem. So gravitons, you have to dress this way. And any other questions?
So this problem is for the soft momenta or collinear momenta?
This is about soft one. Yes.
Still problem for the non-abelian case theory.
Yeah, the collinear still remains for non-abelian gauge theories. Yes. That's still an open problem. Yes.
What do you say the reason for the infinity in the explanation method?
Oh, here.
Yeah,
I didn't say anything. It's just that when you work out the so you have this Hamiltonian. And you have an explicit form of this for each theory that you care about, and you can work out the time evolution operator. So basically, I d over dt of this operator is the Hamiltonian times this operator. You can solve that differential equation, and you get this. The assumption made in textbook was that this was 0 or this is 1. But that's not the case. It is some operator, and because it's an operator, it gives you complications.
So it's from the hard momentum summation.
No, this just comes from the, for instance, in 2ED, for instance, it comes from the 3 vertex, 2 electrons, one.
3 vertex.
Yeah, the 2 electrons and 1 photon. In gravity, it also comes only from the 3 vertex. The 4 and higher order vertices don't contribute. Sorry, how much time do I have?
So you have like 35.
Okay, yeah. Okay, yeah, I didn't mean to suppress any questions, please. Yeah. So, okay, so we talked about soft theorems, higher divergences for the Euclid states. So we have another topic left over, that is asymptotic symmetries. You might have heard about this term in some conferences. And the quick way to understand this is you have some gauge theory, and there are a lot of gauge symmetries. And you mod out by the trivial gauge symmetries. There are some exceptions to this, but I won't go into details. But this is a nice way to view asymptotic symmetries. And you could ask, well, aren't gauge transformations all trivial by definition? And that is not true, because if you follow the Noether procedure to compute the charge of the gauge transformation, what is the defining property of a redundancy? You compute the generator, and it's 0. So it acts trivially on all the quantum states. But if you actually think about that computation, there's one line where you do a partial integration. And there you assume some fall-offs for the fields. And there are some physical modes that violate this fall-off and give you some boundary terms, which gives you a non-zero charge, and therefore it acts non-trivially on the states. And these are physical, even though they are formally gauge. Now, this asymptotic symmetry group is often referred to as large gauge transformations. And this term has been used in non-abelian gauge theory context to refer to topologically non-trivial transformations, which are physical, by the way. But now this definition even allows for topologically trivial gauge transformations that are physical. And in the math literature, these are usually referred to as improper gauge transformations. Okay, so we had, yes?
Yeah. Actually, conventionally, from the Noether process,
Yes.
actually we can get the conserved current.
Yes.
But in the global symmetry case,
Yes.
it's okay.
Yeah, global is fine. These are all local.
Yeah.
Yes.
But in the local case, actually, it's not easy to interpret the conserved current. Instead, we impose a constraint.
Mm-hmm. Oh, yeah. So the constraints shouldn't kill these.
Yeah.
These are physical. Yeah.
Yeah, constraint should kill the redundancy.
Only the redundancy.
Yes. So trivial gauge. What do you mean? Yeah, trivial gauge symmetry.
The redundancy.
Redundancy.
Yes.
So among the 4 gauge symmetry,
yes.
You reduce the genuine symmetry.
Yes.
By eliminating trivial gauge symmetry.
Exactly. That's the way to.
Through the Noether current.
Yes.
Noether charge. Noether current.
Yes.
Noether current eliminate the physical state, right?
Yes.
In the local gauge symmetry.
Yes. Yeah. Yes. Yeah, so if you have some gauge symmetry, and if you are not sure whether this is physical or not, you compute the Noether charge, and if it's 0 on shell, then that tells us that it acts trivially. Otherwise, it is physical. It actually maps one state to a physically distinct state, just like all symmetries do. Okay, so I've talked about all these ancient subjects. Why do I care? Why do we care? And over the past few decades, we worked with ADS-CFT, and there was this beautiful story that concerns the holographic structure of quantum gravity in anti-de Sitter space. And the story begins with the identification of the symmetry and its holographic dual on the boundary, in particular the conformal symmetry. Now, the problem with this is that the real world can, to some approximation, be thought of as flat below cosmological scales. In particular, it's not anti-de Sitter. So it's natural to ask a similar question for flat space. So what are the symmetries of quantum gravity in flat space? So here's a Penrose diagram. We have some complicated interaction in the bulk. I am thinking of quantum gravity in flat space. There's future null infinity and past null infinity, space-like infinity, and there's two time-like infinities. And as we don't really know in quantum gravity what happens in the bulk. And where it happens is also a not very well-defined issue because diffeomorphisms are gauged. But we know how to describe these in the asymptotic past and future, where we can think of space-time as being approximately flat. We just stand very far from whatever is going on. So we think of some metric that is flat to some degree with corrections. And let's say we work with some coordinate r radius from whatever is interesting is going on in the bulk. And here I've used retarded time just to describe space-time near the future null infinity. You can use the advanced time for past null infinity. But we can't just write down anything because we have to have solutions of the Einstein equation. And also we have to choose a gauge. And all this procedure was worked out by the four people, Bondi, Van der Berg, Metzner, and independently Satz. And unfortunately, Van der Berg got lost in the initials, and people refer to this as BMS. And this was worked out explicitly, both of the papers in 1962. So in Bondi coordinates, we have some flat coordinates plus corrections. Here I use capital letters to denote angular variables. And MB here is called Bondi mass aspect. And you may recognize this from, for instance, black holes. If you have black hole of mass M, then it'll sit in here with 1/r, and that represents the monopole contribution here. There's yes
correction comes.
Oh, you write down, you choose some coordinate system, so you fix a gauge, and then you work out the most general corrections in that gauge, and then you plug it into Einstein equations. And then you can solve it, and you find that these are the first non-trivial corrections coming in after the flat space. And this was the work done by these people. There is a correction to the sphere metric. So sphere metric goes like r squared. There's something of order r. This CAB is called the shear tensor. And this encodes the gravitational radiation that goes through to the future null infinity. And this was the reason why these people studied this metric. All right, so we have a set of asymptotically flat space-time. Yes.
Where is the future null boundary?
So once you choose u to be some number and r goes to infinity, that's where the future null infinity sits. But we are doing a 1/r expansion, so we are going a little bit into the bulk. So if we actually take r to infinity, then only the leading term contributes. But now if we go a little bit into the bulk, it's the subleading corrections that come in. All right, so we have a set of these. Notice that it's not unique. We can have different m's, we can have different shears, and there are different corrections at subleading orders. So we have a family of these with different parameters. And we know that the isometry group of flat space is the Poincare group, which is basically space-time translations together with Lorentz transformations. So these authors expected that the group of diffeomorphisms that preserves this structure is just Poincare. And to their surprise, that's not what happened. It turned out to be an enhanced group where the space-time translations is replaced with something called super translations. And back then, supersymmetry wasn't a big thing. So unfortunately, super doesn't have anything to do with supersymmetry. But yeah, this is the term that stuck with in the literature. And what are super translations? They're basically translations, but not constant. They are angle-dependent translations. So there's a function of the angle, f of theta phi. There's some, I wrote down the explicit formula just to give you a taste of what it is. Capital D is the covariant derivative on the sphere. So these are really just functions on the sphere. And you can see that this is an infinite dimensional group because if you have a function on the sphere,
BMS group
Yes.
is defined on the asymptotic infinity.
yes, near the asymptotic infinity.
Here,
Near, yes,
here.
near. Because we are not really on Scry. We are a little bit into Scry because we have corrections.
Asymptotic flat.
Asymptotically flat. So this is flat.
Right.
This is asymptotically flat. This is
Then the BMS group is a local symmetry group or global symmetry?
It is a local transformation,
Local.
yes. It includes the global transformation, which is space-time and Lorentz transformations.
Yeah.
These are global transformations.
In the first part in the metric is actually essentially Minkowskian
Yes,
and the global.
this is global, yes.
So thanks to this, the other two parts actually, so.
Yeah, that makes it work.
Local.
Yes. So these are, notice that these are not isometry group of these metrics. These transformations map one of these to another one of these with different parameters. But these are all solutions of the system. So if we have a transformation that maps one solution to the other, these are called symmetries.
But actually
Yes.
you already gauged away redundant variable by using the boundary coordinate
Yes.
system. But the others are actually, there are still local symmetry, which means that we can eliminate further degrees of freedom.
These are now the physical symmetries. So yeah, these are not the ones that we want to gauge away because these are actual, these are different states of quantum gravity, the different vacuum. And the transformations map one solution to the other. And that therefore they act non-trivially on the states. And these are physical, so we don't want to gauge these away.
Anyway, PMS group is a local group.
This is local.
So local transformation is possible, which means that we can eliminate.
Oh, yes, these are not defined in the bulk. Notice that we have a large R expansion. Yeah, so there's larger corrections here that we ignore. So this is only defined on the bound, near the boundary. Yeah, this is why these are not really symmetries, but asymptotic symmetries. But we expect them to be symmetries of quantum gravity, where we have really modeled out the fields in the bulk. And the only observables we know in quantum gravity are stuff that we define on the asymptotic
It
boundary.
means almost global. PMS group is global.
It's local in the sense that they have some coordinate dependence. Yeah, the verdict of whether these are gauge or not is you compute the charge and you find that it is non-zero. But yeah.
Charge is non-zero means actually global symmetry. Local symmetry case actually zero. Because in local case actually, every conserved quantity should be the generator.
So this is a little bit more confusing in the context of gravity, but if we can repeat this exercise in QED. So what we find is that, you can argue that all phase rotations or all U1 gauge transformations are local. If they are local, then they are trivial. But what happens is that if you have a gauge function that only depends on the angles, then they don't decay away at infinity because there's no 1 over R. So if you compute the charge of that gauge transformation, that charge is non-zero, even though it is local.
Really?
Yes. So this is really like a special case. And actually this was known earlier in the literature as improper gauge transformations. So if you have a manifold with a boundary.
Okay, I see.
Yeah. Yes.
So the Lorentz transform is 3D Lorentz or 4D Lorentz.
4D Lorentz transformations, yes.
But you are sticking to some boundary near infinity. No?
Yes.
So it's essentially 3D.
Yeah, although we are going a little bit into the bulk, we are not really on Scry. We are going a little bit into the bulk. So 1 over R really matters.
How many generators of the Lorentz transform generators?
6.
6.
6 for this, 4 for this, so 10. 10 global transformations, which is enhanced to an infinite number plus 6. And infinite, because a function on the sphere can be expanded in spherical harmonics, and there's an infinite number of those.
Just a question.
Yes.
You said there are corrections in higher orders.
Yes.
So you presented the orders in a consistent way, like you keep track of the entry to that order. This is.
Oh, no. Actually, I dumped away some stuff.
Ah.
Yeah, but yeah, I can talk about more terms later. Yes.
The embodiments are related three-dimensional spatial.
Yeah, so among the the three dimensions, there's a radial direction and there's two angles. So these are the two angles. And if you expand this in spherical harmonics, you have the lowest spherical harmonic, the L equals 0, that gives you time translation. And what is not really clear from this, but it really works, is that if you look at the L equals 1 spherical harmonics, there's 3 of those. Those exactly correspond to the space translations. And then there's L equals 2 and higher, which now do not have any correspondence with the global transformations. These are really generalizations.
Psi mu is a killing me.
Psi mu is, oh no, this is not a killing vector. If it's a killing vector, then it's an isometry, right? But it is to be stressed that this is not an isometry. This is a transformation that maps one of these to another. So it transforms the metric.
It's not an isometry.
It's not an isometry, but it preserves the structure. Yes.
So I have two questions. The first of all, does the vector psi form a certain linear?
Yes. So this forms an abelian group. I'll talk about a generalization right in the slides, and together, yeah, it forms a group. Yes.
So the quantum gravity is really hard to establish because the passing measure of the gravity is not well known. But some people, maybe include you, I'm saying that the passing measure of gravity should contain some boundary condition, such as the asymptotic ADS and asymptotic flat.
Yes.
So is the BMS group is the BMS group is the gauge group of the quantum gravity, which assumes that the asymptotic flat as a boundary condition.
So one thing that the BMS is not a gauge symmetry. So we don't want to gauge this. This is an actual symmetry of quantum gravity. Well, in flat space. So we think of one of the quantum gravity.
Not in the flat space, but asymptotically.
Asymptotically. Yes. Yes. Yeah. In quantum gravity, specifying things in the bulk is. Yeah, it's just not.
It's local, but not gauge.
Yeah, not gauge. Yes. Any other questions?
So every function is f and the psi is related.
Yes, psi, there's one psi for every f. Yes. And there's an infinite number of those.
And you said that the DNS group changes the metric, but preserves the structure.
Yes.
What do you mean by that? Which one is invariant under the DNS?
Oh, so C, we have to put that some value. Let's say 2 in some units, and then we do this, and you can transform it to 3, but it's still of this form. Yeah.
So metric is always in that form,
Yes.
but the coefficient can be changed, including the m sub p.
Yes, ME, on the mass aspect and the shear. We know exactly how they transform under this. Yeah.
In that sense, it looks like isometry.
Except that isometry means we fix a metric and it goes back to self. But now we have a family of metrics where we are mapping one to the other, and it would have been an isometry if we gauged this. But we don't want that.
Anyway, there will be some corresponding consumed charge to infinite dimensional group.
Yes. Yes. There's a super transition charge.
Why do you call super?
Oh, that's the term that these people put to this transformation. It has nothing to do with Suzy.
So there are super translation conserve the super translation charge.
Charges, yes. And conserve, we will, it's not conserved in the usual sense because these are not defined in the bulk. We'll know what it means by conserved in a bit. Yeah.
You have 15 minutes.
Okay, now the initial derivation was in a coordinate dependent way. Later findings in the recent years in 2014 and onwards found that you can also enhance Lorentz transformations to an infinite dimensional group, where you think of, instead of Lorentz transformations, you think of diffeomorphisms in the sphere. And what that changes is now you allow this round metric to deviate from sphere metric, but these are all diffeomorphic to each other. So it looks as if it's not flat in a coordinate dependent way, but you can write down coordinate independent formulations of these, and you will find that actually you can also define this enhancement called BMS super rotations that enhances Lorentz transformations. So in complex coordinates, the vector field, you can think of 6 vector fields, which correspond to the 6 Lorentz generators. But now, if you think of a generic function on the sphere, then there are an infinite number of these. Now, super translation together with super rotation extended this way is called generalized BMS group. And there is a BMS algebra that is non-trivial. You have 2 super translations that commute. Super translation with super rotation gives you another super translation. 2 super rotations give you another super rotation. This is spelled out in the paper of Barnich and Frossart in 2011. If you're interested, I can point you where this is worked out. Nowadays, people usually refer to the generalized BMS group as just the BMS group. Okay, so BMS transformations are symmetries of flat space quantum gravity. And as a low energy effective field theory, we know how to do S-matrix computations in perturbative quantum gravity around flat space. So you expand around flat space some spin 2 field, and BMS charge must be conserved in this sense. You have some incoming state scattering into an outgoing state. The BMS charge of the outgoing state should match the charge of the incoming state. Now, remember that this is an infinite symmetry group, an infinite dimensional symmetry group. So this presumably imposes an infinite number of new constraints on gravitational S matrices. And presumably there's a gauge theory analog of this. So we have an infinite number of new constraints for QED. Can this be consistent? Actually, the soft theorem, it turns out, is a clever rewriting of this equation. This equation you plug in the expressions for Q plus and Q minus, and you just get this. And you see there's one soft theorem for each direction on the sphere that corresponds to the direction of the photon momentum and graviton momentum. And each direction, you sum them up into some generic function on the sphere. And therefore, soft theorems are conservation laws of super translations, the super translation symmetry, written in a different way. Well, that's all great, except that S matrix does not exist. There's wire divergences. Well, up to that fact, this correspondence between asymptotic symmetries and soft theorems has been worked out in many different aspects, case by case. So the leading soft theorem, leading soft graviton theorem, 3 levels of leading theorems for gravity and photons, and then higher dimensions, supersymmetry, whatnot. And this is the work that has been done mainly in 2014 to 2017. Now, we have a conserved quantity in scattering amplitudes. So if we have a conserved quantity, it's usually a good idea to implement that as a quantum number for the states.
So could you give some pictures in your previous page?
Yes.
With this PMS symmetry, that is essentially this rewriting of the soft theorems.
Yes.
Could you just how to understand those things qualitatively?
Oh yeah, that's actually quite complicated. So this is a charge on the future null boundary. This is a charge at the past null boundary, and actually they break into 2 parts. It has a term that corresponds to a soft graviton, plus a term that corresponds to the hard matter. And if you collect the graviton, oh no, the hard particles.
Usual hard particles.
Yes. The charge has some low energy part and a finite energy part. And you can collect the low energy parts together, and those correspond to an insertion of a graviton with the soft limit taken. And the hard part precisely corresponds to this. And of course, you cannot see that from this, but that's some lines of computation there. Yes.
Is the soft factor has a divergence, then that the in and out state has
Yes.
also divergence?
This charge, when acting on the in state, can have a divergence, but actually there's secretly one factor of momentum outside that cancels the divergence. So yeah, this equation is finite. And that's because there's a soft factor multiplying k, well, k0.
Soft is theorem, the soft factor diverge, right?
Yeah, so I guess to be more precise, this equation corresponds to soft theorem times an overall factor of k0, which cancels the 1 over k here. Yes.
So can you go back to the last slide? Yeah. So here you said the matching between leading and subleading, but I guess that means that does not mean that EMS translation only applies to leading.
Oh yeah, this only corresponds to leading.
Oh,
And then there's a subleading term.
yeah.
So leading was 1 over k. Subleading term is k0 at tree level. That actually corresponds to superrotation.
For example, then subleading, that orders cannot be explained by EMS.
Oh yeah, they will introduce new symmetries, and this is the work that I am doing.
Oh.
Yes. Hopefully I'll have time to. Yeah. Okay. Right. So we have a conserved quantity, and if you have conserved quantity like momentum, it's a good idea to organize states as eigenstates of these. The problem is that if you organize states into eigenstates of supertranslation, they don't give you momentum eigenstates. Instead, what you find is that you find a coherent state where particles are dressed with soft gravitons, and we've heard of this. It matches exactly with the IR finite for the Euclid states in perturbative quantum gravity. And there's also a analogous case for QED. And we find that the amplitude is non-zero. That is, the IR divergence is cancelled if and only if the supertranslation charge is conserved. So this is an asymptotic symmetry view of why the IR divergences were happening. We were working with states that violate a conservation law. And yeah, this is where I entered the field. And this was the first paper that I wrote in the field. Yeah. In the lieu of time, I'll just briefly run through what I have. So I have some slides that describe what I was doing. How much time do I have?
10 minutes.
10 minutes, okay. Yeah, so from here, I was working on different aspects of these asymptotic symmetries, soft theorems, IR divergences, and whatnot. In 2016, there was a paper by Hawking, Perry, and Strominger that argued that black holes have soft hair in contrast to the null hair theorem. And what we have learned is that the correct asymptotic states are for the Euclid states. They aren't momentum eigenstates. So we can compute what the correct scattering states on the horizon are. And these would be the states that you use to compute scattering in the black hole background. And this was worked out by, at least perturbatively, in around at the end of 80s by many authors. And we can use these results to compute the Euclid dressings and see what happens. And actually, it turns out that the dressings carry a definite supertranslation charge. And what this tells us is that the origin of this proposed soft hair, which was unclear until then, we could show that this is the remnant of all the matter that fell into the black hole. So actually, the black hole horizon knows a history of all the particles that fell in, and this is kept track of by the soft hair. And again, yeah, this was something that I worked on after a few years. There is a topic that I'm working on recently, and this has to do with loop corrections to soft theorems. We saw that there was a divergent leading soft theorem that went like 1 over k, and you can show that that's exact to all orders in the loops. But once you go to subleading orders, things become a little bit tricky, and it used to be that only the tree level result was known. In 2018, Ashok Sen and his collaborators had his magic hat, and they've shown using explicit Feynman diagram computations at loops that you get a one loop exact correction that goes non-analytic in the soft energy. So now I have separated out the the time component of the energy, called it omega, and there's a term that goes like log omega. So we have a new soft theorem, and we have strong evidence to believe that this gives us a new symmetry. Well, it turns out that it's not really a new symmetry.
So
It
when
is-
you say massive fluidity, you mean massive?
Oh yeah, massive electrons,
Electron, not the.
not photons. Yeah, yes. And yeah, in all these stories, it's crucial that the gauge bosons are massless. Right. So it took us some years and some series of papers to show that actually this subleading non-analytic term corresponds to BMS superrotation with long-range interactions turned on. In the earlier papers, BMS supertranslation, people only computed at tree level. You ignore all interactions, and you find that it gives you some tree-level subleading soft graviton theorem. But once you include loops, it gives you higher divergent contributions, and that gives you exactly this term. Yes?
The roots is the root of the soft particles or the hard particles?
Oh, yeah, soft particles, yes, yeah. Well, not exactly. So loop of the graviton. So you have a graviton, you have a diagram. This is a diagram that gives you that term. There's another diagram. So you can think of massive scalars coupled to gravity. And these are massive scalar legs. And there's some graviton loop here. So because the momentum here is k, and this is p minus k, right? So this loop knows about the momentum of this. And it's this loop where that log omega arises.
So we don't see logs of the theorem in photon case, and so yes.
Oh no, there's a photon story. It doesn't have this.
But then it was generalized by BNS for translation.
Oh no. So at leading order there's a large gauge symmetry, but at subleading order there's some gauge transformation that is divergent that you can work out to obtain the subleading log-soft theorem. That was one of these first two papers.
Yeah, my question is that logs of the theorem always related to BNS for rotations.
In gravity. BMS superrotation in gravity, not supertranslation.
That's then in photon case, that gravity, that logs of the theorem is related to which symmetry?
Oh, in soft photon theorem. So you have a gauge transformation that diverges. So in the UR coordinates, you have a function that is linear in R, and you work out the conservation law, and you will find that you get exactly this.
So excuse me, so usually you mentioned that kind of loops cancels the IR divergence, right?
Oh,
Is that
no. These are different stories. Yeah. So there's some IR divergence coming from these, but here it's a different computation. Yes.
different from the
Yeah, it was different from the block-norsing method that I was mentioning earlier. Yeah. These are different computations.
I wonder if that's big.
Oh. Yeah, in this, yeah. No. So yeah, I was secretly gonna jump over this, but so let's just deviate from flat space. I want to show you that actually this perspective of symptotic symmetries has applications in other stories as well. And here I want to illustrate some story that I worked out with Finn Larson a couple of years ago. So Jackie-Teitelbaum gravity. This is a two-dimensional dilaton gravity model that serves as the universal near horizon theory of near extreme black holes in higher dimensions. So you take some higher dimensional theory, you do a dimensional reduction in the black hole background, and you obtain this universally. Now, you see that the bulk is linear in the dilaton. So the dilaton equation of motion becomes a constraint, and it fixes the bulk into ADS2. And there's some solution for the dilaton as well. So you may think, well, if R plus 2 is equal to 0, the on-shell action is trivial. But actually, what Madasina and Yang showed was that that's not the case. There's some non-trivial conformal structure at infinity. And you can probe this by regulating ADS. So now we have a disk with some wobbly boundary that is embedded into ADS2. And you can write down the embedding in this form.
At the boundary, the conformal symmetry is local and global.
The conformal symmetry on the boundary. So we have a global SL2.
Global SL2.
Yeah. But now there's local symmetry that is broken by the Goldstone mode, which is this. So we have some global, we have some symmetry that is broken by the choice of the wobbly, the embedding that encodes the conformal structure that sits at infinity. And it's this conformal structure that gives rise to a Shortzian effective action. And this was a very famous result in like 2016, and you may have heard this in one talk or the other.
Global SL2.
There is a global SL2 that has to be gauged because the Shortzian of SL2 is 0. So yeah, those the action is inert under SL2 transformations.
Why do you consider closed it?
Oh, because we are in Euclidean signature, and Euclidean ADS2 is topologically a disk when you regulate it. So there's a circle.
S1.
Yeah, there's an S1 circle. Yes. Now let's put on the asymptotic symmetry hat. So what do? We take the simple ADS metric, that is this, and we ask, what is the most general diffeomorphism that preserves asymptotically this plus corrections? And this is something that I've worked out with Finn. You get something that truncates. In Pfefferman and Graham gauge, you can go to other gauge, but it'll usually truncate. And you find that the metric is given in terms of a Shortzian derivative. And this function represents the non-trivial conformal structure at the boundary. So with this metric, you can use an exact circular boundary because these are redundant. You can do an active diffeomorphism to straighten out the circle, and you will get this metric near the boundary.
In this sense, the conformal structure at the boundary seems to be local. Because
near the boundary, yeah.
In connection with the diffeomorphism.
Yeah, but now this is only defined near the boundary. So we have sort of just moved the circle into, we have moved to a coordinate system where the wobbly boundary looks as if it's a circle. The price you pay is that the metric becomes wobbly. And now you plug this in to compute this, you get exactly the same thing. So these are the same, yeah, these are two sides of the same coin.
So one-dimensional parametrization persists here, I think.
Yeah, yes.
So
And in the metric.
sense, local.
This is local, yes. Yes.
So in this sense, I'm now actually the conformal symmetry would be a local symmetry.
Yes, but this is now broken. So this is the Goldstone boson of reparametrization that is broken. And this action describes the dynamics of the Goldstone boson. Yeah. So I'm in a bit of a hurry, but so what I want to say is that the asymptotic symmetry hat gives us the same result as the classical derivation given by Marcina Yang. And this is good. Now let's come back to 4D flat spacetime. And we can do the same thing. We have BMS symmetry. And once we pick an asymptotically flat metric, that's the vacuum solution of Einstein gravity. And
what is the connection of BMS with the previous Schwarzian?
Oh yeah, so that's what I'm trying to come up. Yes. So we have a symmetry, the BMS symmetry, but once we pick a metric, we have broken the symmetry. So the vacuum breaks the symmetry. So this is a sort of spontaneous symmetry breaking. And what that tells us is that we can write down an effective action as just like the Schwarzian action. And this form of the action was already known by Dan Kapek, Paramitra, and Temple Hay a couple of years ago. We are now working on a generalization such that all of the stuff that we talked about earlier, soft theorems, higher divergences, asymptotic symmetries, these can be computed just from this effective action. And we don't even have to allude to the bulk. So you can think of this action as some holographic dual, at least in the soft sector of 4D bulk physics. And I was told that this paper will appear tomorrow because he submitted it today, but I hope that really happens. So yeah, that's it. And yeah,
sorry, this
yeah.
N and M plus, they are supposed to be this your previous small NB and this shear S.
Oh yeah, so sorry, I haven't specified what these are. So the here is some derivative of the C. So this C is the Goldstone boson of BMS transformations. So under a BMS transformation, under a BMS supertranslation, which is parameterized by a function f on the sphere, this C shifts by 2f. So we really are sitting in some Mexican hat where
But
each
this
point.
variable is a fluctuation of metric.
Yes, yes. So these are really the Goldstone bosons of the broken symmetry. And N is the conjugate partner, the symplectic partner of C. Yeah.
That actually equation how that is related to JT.
So in JT gravity, we had a diff S1 symmetry that is broken by choosing a metric. The metric forces us to choose an F. And these are vacuum solutions of the dilettante gravity. And this, when we can put this in to the action to get the on-shell action, the bulk vanishes, this gives you the Schwarzschild action. And that action describes the dynamics of the Goldstone boson that breaks the diff S1. Here, we have a BMS symmetry broken by the choice of the metric. And the effective action describes the dynamics of the Goldstone boson that is C.
Why do you have 4 derivatives?
Because this is in gravity. In gauge theory, there's one. In the shear, the shear had 2 indices. Solving Einstein equation and imposing some constraints tells us that this is 2 derivatives of a function. So yeah, 2 DADB acting on shear.
As a solution to
Einstein equations, yes.
What happens if you use, instead of U, actually V?
Then you get stuff on the past, and you have to do both because the plus are modes on the future and minus are modes on the past. So in order to derive this, you have to do both of the charts.
You have told that the action I may be the dual CFT of the the gravity.
Soft sector only.
Yeah, but just let's see. So the Schwarzschild action is not the ADCP dual of the JT gravity. It has only a classical correspondence, so it does not reveal the full quantum behavior.
Oh
of
yeah,
the
yeah.
gravity.
So this is only an analogy, yes.
This action I should also be, has maybe some kind of the classical or the semi-classical, appearance of the, the bulk gravity. And also you have mentioned that, so it might be the dual safety of the soft sector.
Only the soft.
Which means the ion limit. So it should not be the full safety dual. So there should not be that.
No. I'm not saying this is the CFT dual or anything. This is just a theory, a 2D theory that can describe everything infrared that goes on in scattering amplitudes of 4D in the soft sector.
In certain limit, right?
In only in the small energy limit, yes.
So here the X is the TR or is it phi?
Oh, this?
Yeah.
This data phi. Yeah, these are all on the sphere. And the fact that the sort of dual action is described on the sphere, on the celestial sphere, is the reason why this field gets named celestial holography. But as correctly pointed out, it's not. We don't really have a satisfactory holography yet. So this is still in the works.
Bondi gauge is actually a gauge fixing.
Yes.
So this is not a SSB. So why does the Goldstone mode appear?
So Bondi gauge doesn't completely fix the gauge. Yeah. There's some remaining.
You mentioned the Goldstone mode in the previous here.
Yes. So we had some asymptotic
So it has nothing to do with the gauge fixing condition. No.
Actually, that's a good question. All of these, because they are physical, you should be able to derive all of these in any gauge. But it is sad to say that this derivation is only given in 2 gauges. One is harmonic gauge and the other is Bondi gauge.
It means gauge fixing condition has nothing to do with the Goldstone mode.
That's the expectation that has to be proven.
So in the previous, actually, in the at the boundary Schwarzschild, you mentioned actually it's a Goldstone mode.
Yes.
Goldstone mode. So I'm wondering why the Goldstone mode appear. So seemingly actually after gauge fixing, so Goldstone mode type actually appear. In any gauge, we can produce the Schwarzschild.
Yes. There I chose platform and grand gauge, but
we call the Goldstone mode. What is the reason?
Because you have a symmetry that is broken by the vacuum.
Broken
And-
means of SSB or express gauge fixed?
No, spontaneously broken.
Spontaneous.
Yeah.
So where is the SSB? Here, in Schwarzschild.
No, not in Schwarzschild, but in here, right? That action had to do with this.
That is SSB.
Because the choice,
Yeah.
there's an infinite number of vacuum for different values of these.
This
Then what
person is just a gauge fixing, explicit gauge fixing.
Oh, no. In deriving this, we have to choose a particular gauge. But we could choose a different gauge where these will sit in some other components, but they are related by different small different that is.
So those correspond to just a mole.
Yes, now this thing, so the thing that is broken is BMS supertranslation. And you can show that this shifts under BMS supertranslation. So we have picked a vacuum. Any vacuum would have been fine. But now supertranslation
Yeah.
shifts to another vacuum. Yes. Okay, so I think I went over time, but
Wrap up.
yeah.
Yeah.
My goal is to explore this further. Basically, we've worked out something that corresponds to BMS symmetries, supertranslation and superrotation. But now it has been shown by Ashok-sen and other collaborators that not only do we have the log-soft theorem, but we have an infinite tolerance. And this has been proven explicitly for classical point particle scattering. But to the first few orders, this has been computed using Feynman diagrams. So an infinite number of soft theorems. So do we have a larger group of symmetries that is infinite dimensional that includes BMS transformations? So this is the bigger picture that I want to get at ultimately. But like right now we are working out this term. Yeah. So the computation was done classically. Can we do Feynman diagrams? Do we have asymptotic symmetries that include BMS? These are the kind of questions that I want to ask. Thank you.